about population when we have many samples. Okay, so this is very useful in statistical, predictions, making predictions using statistics. This is very useful. So the central limit theorem actually proposes two things. Mean of all sample means from a given population will be approximately equal to the population's mean. What this means we'll see. And the second thing is sampling distribution of means. Sampling distribution of means approaches normal distribution with a mean of mu, right? Population's mean, and then a variance of sigma square by n, or standard deviation of sigma by n. What is standard deviation? Square root of variance, right? When you apply square root to this, it's going to be sigma by square root of n. N is the number of samples. Number of samples in each of those, n number of samples. Let us look at one example to get more clarity. So if you see this, the mean of all sample means from a given population will be approximately equal to population. What this means, we want to see. Central limit theorem already proving this. It is proven, right? So whenever you get multiple samples, right, you can actually take mean of it, and then you can say that is the population's mean. Like, whatever, this is actually proven thing. So what this means, suppose that there is a population size of 2 lakh apples, 200,000 apples. Okay. Population mean and population variance, right? Mu is the population mean. Sigma square is the population's variance. Standard deviation is sigma. Okay. This is notation. Okay. So suppose that each sample with 36 apples, right? There are many samples were taken. One sample, 36 apples, second 36 apples, fourth 36 apples, like that many samples were taken. Okay. Now the mean of all these means, right? The first sample's mean is mu1, second sample's mean is mu2, third sample's mean is mu3, like that m number of samples were taken. Okay. So mu m. When you take average of all these samples, right? All these means, that is going to be equal to the population's mean. That is what the statement means. Mean of all sample means from a given population will be approximately equal to mean of the population. So no need to know the population's mean. Suppose that there are in a state, a state is producing apples, and you wanted to know mean, average size of the average weight of the apple. Okay. No need to take all the apples weights individually. Can we take individual apples weight throughout the state? Can we? Did you get the problem statement? I wanted to know average weight of the apple in a state produced, where the apple is produced. Can I take each apple, harvested in the state and weigh it and take an average?
No.
No, right?
It's not possible.
So practically impossible. So how to know that? The only way is that, take, sample of, 36 apples from one place, 36 or maybe 100 apples, 100 apples, 100 apples, like that. In different places, take 100 apple samples, 10,000 samples you take, right? 10,000 samples you take, and for each of those samples you take mean weight, right? 100 apples you can take mean weight, right? Each apple, 100 apples, each apple you weight, note down, and then take the mean of it. Like that you take means and then calculate mean of all those means. That is going to be equal to population's mean. This is proven. Okay, this is proven. So they did like, small sample, small, populations of small size, and then took small sample sizes and then did this experiment, and it was proven in many cases. So it is taken for granted. Okay, that is the first statement made by central limit theorem. Okay, we can take it for granted. Any questions here?
No, sir.
This is called as a sampling distribution. Right? This is, whatever the means you are actually looking at. If you try to plot it as a, as a bar graph, We call that as sampling distribution of means. Okay, so so there is mean mu1, right? Mu1 may be 10. Okay, if you take 10, there may be two sets of apples which have got 10 mean. There may be 20, and there may be 4 sets of apples, 36 sets, 36 samples, which have got 20 mean. Now 30 mean, there may be 6 samples, 36 samples, which have got 30 mean, like that, right? If you try to do distribution plot of these means, you call that as sampling distribution of means. Approaches normal distribution. So this is always true. When you take n number of samples and take means of them and try to plot the bar graph of those means, sample means, it is going to be normally distributed. The sampling distribution of means we are trying to see how the means are distributed, how the samples means are distributed. Samples means are distributed. These are the samples and these are the means. The samples means are distributed in normal, right? Normal distribution. Samples means are always normally distributed. That is second statement. Samples means are always normally distributed. Whether your population is normally distributed or not, it doesn't matter. Your samples means are always normally distributed. This is one important thing to know. Okay. You got my statement. I made one statement. Whether your population is normally distributed or not, it doesn't matter. Your samples means are going to be normally distributed, I said. Did you get the statement? Did you get the statement? Huh?
Yes,
so what I meant by population, whether the population is normally distributed or not. If I have to do a plot of population's normal distribution, what should I take on x-axis and what should I take on y-axis? If I have to do a plot of the population, what should I take on x-axis and what should I take on y-axis? I should take apple weight, right? Each apple weight I should take on x-axis, right? So let me try to. So you need to understand this. Based on this, right, we will actually solve some mathematical problems now. Why are we solving them? We need to get a complete hold on normal distribution and central limit theorem. We need to get complete hold on it. Okay. So it is like we understood some part and we'll understand later, not going to work. Okay. So if I have to do a plot, if I have to see whether the population is normally distributed or not, what is the thing we are looking at here? The weight, right? Weight of the apple is the thing we are actually looking at, right? So on the x-axis, apple weight. Okay. On y-axis, count, right? Or probability. It doesn't matter, right? So you take, apple weight maybe 30 grams or maybe 20 grams, 30 grams, 40 grams, 50 grams, 60 grams, 70 grams, like that. So there may be some apples, maybe 20 gram apples are maybe more, 30 gram apples may be less, 40 gram apples may be more, maybe 50 gram apples may be a little less, right? Like that maybe, data may be distributed like that, right? Population data may be distributed. But when you take the, when you actually draw the graph for the bar graph for means, right? Means of the samples, right? What is an x-axis here? Sampling distribution of means, right? This is sampling distribution. What is an x-axis? Means, right? So means, yeah, sample means, right? If you understand this, right? Next 2 classes are going to be very easy. Okay. So if you take this, right, it is always going to be normally distributed. Irrespective of the population's distribution, whether it is normal or not, irrespective of this is going to be normally distributed, right? When you take multiple samples and take means, it is going to be normal. When the data is normally distributed, you can make many inferences from it. We'll use this. 2. Now first statement, right? When you take many samples and take means of them, and mean of all those means is going to be population's mean. This is useful in doing the exit polls. You got the point, right? These are all samples collected from different villages, okay? And took means or mode, and then took mode of all those modes, and you can see who is going to win in the current next election, right? This is the this central limit theorem's first rule is useful in doing the exit polls. Got it? Got it? Any questions on this? Okay. So it doesn't matter whether the population is normally distributed or not. Sampling distribution of means is going to be normally distributed. What we call this as sampling distribution of means. Okay. So samples means distribution. I don't know why they named it like this. Sampling distribution of the means. Okay. With a mean mu, right? A mean mu, I am saying. What is mu? Population's mean. Okay. Of all these means mean is this, right? Is going to be equal to the population's mean, right? So the sampling distributions means mean is going to be mu, right? Sampling distribution of mean is going to be mu, right? Somewhere here it's going to be, and then variance is going to be sigma square by n. What is sigma? Population's standard deviation or population's variance. Okay. What is n here? N is the number of samples in each of the sample. Number of samples in each of the sample. 36 is going to be n here. Got it? Got it? Right? That is central limit theorem. So let us look at one example now. Right? I will actually run a video which will have a normally distributed population from where we'll take multiple samples and then try to do a sampling distribution plot, right? Distribution plot of the means, and it's going to be normally distributed. When you take less number of samples, the spread is going to be more. When you take more, more samples in each of the more items in each of the sample, then it's going to be steep. Okay, let us look at that video. Give me 1 second. I need to put that. I need to bring it out. So if you look at this data, right, the population is normally distributed. I made one statement. Whether population is normally distributed or not, the sampling distribution of means is going to be normally distributed, right? This is a population with a normal distribution. Now, right, I am going to take a sample of five items from this population, right? Sample of 5 items from this population. So when I click on animate, so 5 samples I have taken and took mean. 5 samples I have taken, took mean. Again, I am going to take 5 more samples. Right, that is mean. But I am going to take 5 more samples, and again mean I have taken. And as soon as I took the mean, right, I am actually plotting it on the distribution plot. Okay. So on the second set, right, I am taking 20 samples. So this is what I am trying to explain here is, in your sample, if number of samples are more, the normal distribution is going to be steeper. When it becomes steep, right, the predictivity improves, right, because the data is going to be very close to me. Okay, so I took 2 sets of sampling distributions, one with 5 samples, sample size of 5, second with sample size 20. right? 5 samples mean, 20 samples mean. Again, I am animating. 5 samples mean, 20 samples mean, 5 samples mean, 20 samples mean, right? Again, 5 samples mean. Like this, you take many samples, right? Now I am going to do 10,000 samples in a single shot. When I click on the 10,000, right, it is going to take 5 sample sized 10,000 samples, 20 sample sized 10,000 samples. For each sample, it's going to take mean and plot it on this and this. And we'll see a normal distribution. Let's see. Right? See that? A normal distribution came. But when you look at that plot, right? See that there is some, no, here and there thing is there, right? It is not perfectly normal. If you take too many samples, right? 1 lakh samples, if you take, it is going to be perfectly normal. Okay. So when number of samples increase and sample size increases, the sampling distribution of means normal distribution actually improves. Okay. Normal distribution behavior improves. So the mean here on this, 5 sample is 116.01. On the population, right, it is 16. We have taken a population where we know mean and standard deviation. Right? In general, when you are in real time, right, you will not know the population's mean and standard deviation. But we'll take best approximations of sample, population's mean and standard deviation. Okay, in real time, when you are trying to do exit poll survey, you will not know who's going to win. But from the samples, you have to actually derive it, right? But in this scenario, whatever I am trying to show right now, we know the population's mean, population's mode, population standard deviation and all, and we are experimenting and see whether this theorem is true or not. Whatever the theorem is saying is true or not. And the second, 20 sample, sampling distribution, the mean is 15.99. Okay. So it is median is also kind of, so right on the, so when you look at this standard deviation of the population, it is actually 5. The standard deviation of the sampling distributions is calculated one. We call that as um, standard error. The standard deviation is calculated using x minus mu sigma I is equal to 1 to m x minus mu whole square divided by n m square root, right? That's how we calculate the standard deviation of a data. Whether it is means or data, we will calculate that like that. But we can calculate this number using this formula. We can calculate the standard deviation using this formula. That is, if you calculate standard deviation of sampling distribution using this formula, we call it a standard error. Okay. The standard deviation of the sampling distribution of means calculated using this formula is called a standard error. If you calculate standard deviation of the sampling distribution of means using original standard deviation formula, you call that a standard deviation. In this,
Sir,
yeah.
standard deviation can also be found by taking the square root of the variance, sir. Is it right?
Yeah. That is the formula. Actual formula is that only, right? Variance we looked at first and then we looked at standard deviation. Why did we do square root? Because variance is not variance is in the squared units of the original data. If your original data is centimeters, right? You took centimeter minus centimeter, right? The data point is centimeter. Mean is also in centimeters, right? You took difference, that is centimeters, and you applied square. For each data point you did, you summed it all and took average. That is variance, right? Is that
And
correct?
okay, sir. And why do we use this formula here, sir? Divide by
You
n.
This is like, either way you can calculate a variance of this sampling distribution of means. It is not true for the original data. This
Okay.
formula can calculate standard deviation of sampling distribution of means only.
Okay.
Okay, I'll come to that. Give me like 2 minutes and let me complete this whatever I am talking here. Then I'll come to this and I'll show you clearly with example. I'll show you. Okay, this is a
Okay.
bit confusing thing. I try to make as easy as possible by drawing pictures and all that. We'll see. Okay, give me like 2 more minutes. So here, right, we can calculate this standard deviation belongs to these means. What are these? An x-axis, they are means, right? So you can calculate standard deviation. What are means? They are numbers, right? For these numbers, I calculate standard deviation. How to calculate standard deviation? Square root of x minus mu whole square divided by sigma is equal to 1 to m x minus mu square divided by m, right? Using that I calculated, but this number can be calculated using this formula also. This applies for only sampling distribution of means. This formula to calculate variance or sigma by square root n is going to be standard deviation. Applies only for sampling distribution of means. Original data it is not going to apply. Okay. Now let us we have taken a normally distributed population and we took 5 samples. 5 samples of 10,000. Sample size of 5, 10,000. Sample size of 20, 10,000, and tried to take means and plotted, and we found that they are normally distributed. Now we are going to take a population which is of not non-normal distribution. Okay, so I am actually creating one population which is of not normally distributed, right? You can say that this is not normally distributed, right? Because it is not forming bell curve. Now I am going to take samples from it. When I take 5 numbered samples 10,000 and 20 numbered samples to 10,000, even when the population is not normally distributed, sampling distribution of means is going to be normally distributed. See that. I have taken 5 samples, 20 samples, 5 samples, 20 samples. This was a tool by some organization, and it was not working on new window, new browser. So I just recorded it. See that 10,000 samples I have taken. Even when the population is not normally distributed, the sampling distributions are normal. And if you look at carefully, on this, the spread is more. When the sample size is less, the normal distribution spread is more. That means the standard deviation is going to be more. On this, when the sample size is big, the spread is less. Right? Spread is less means data is going to be close to mean. Data is going to be close to mean like that. Okay. So this is the central limit theorem, and this is a kind of simulated example which actually tries to prove that whether the population is normally distributed or not, the sampling distribution of means is going to be normally distributed, and how the samples are chosen, how you do the plot is all showed in visually. Okay. So I'll come to Ganga Devi's question, but any other questions?
Yeah, sir, here in both the cases where sample size is equal to 5 or sample size is equal to 20, total population is constant, right?
Total population is constant only. Total population, we shouldn't be saying constant. Population is ever growing. We don't know what is happening with the population, but we took some samples.
No, in this example I'm asking.
In this example, yes, but in real time or in this example also you should think, right? You should think like that, because if you look at voters, right? Some people will be entering as voters right now. Some people will be exiting as voters right now, right? Some people are passing away. Some people's age is actually, 18 or 21, I don't know. So they are entering 21, maybe they are taking, voter IDs today, right? Voters will be ever changing, that is, right? So from that, whatever you have, you will take. Right, you will take sample taking doesn't require whether data is growing or not, right? Did you get the point?
Yeah, sure.
Right, this point is very important. Actually, you asked a very right question, right? When you are building a model, you always take sample. When you are actually training a model, you always take a sample and try to experiment with that, because you cannot take population because it's ever growing. If you take an application and database, application will be dumping data every second. If it's really a big application like Facebook, every microsecond you will get millions of records, right? You cannot take population and build a model. Always you take a sample. It may be 1 million records or 1 billion records. Always you take a sample and then train a model. Once you know that this model is going to work, right, then you are going to put it onto server and maybe do a continuous integration build kind of a thing, right? You take the current fresh data every time you try to push it into the model and see how it's working. If it's not working well, and compare it with the real results. If it's not working well, you will retrain, right? So that is like DevOps kind of thing. ML ops we are calling it as. In recent days, in interviews they are asking it is called as ML ops, right? So like you got right what I'm actually trying to explain.
Yeah, yes, sir.
I may actually go into other areas, so try to control me. Okay. So any other questions? Okay, so let us jump back into the slide and show, right, and try to explain whatever the Ganga Devi's question, madam's question, right? So here the population, right? I've taken 10,000 samples. Each time I took a sample, 5 samples, I took mean, and that mean was like, it is like 16, around 16 here, right? So 14. 14, sorry, 16, 15, 14, 13, 12, 11, and 10. So there are around, I think around 500 samples, around maybe 400 samples, which are actually falling at 14 mean. 14 mean. If you take 5 numbers, 5 numbers, 5 numbers, right? The mean of those 5 numbers is actually falling around 500 times, 400 times. It is around, right, like that. So I am trying to take an x-axis, those mean values on x-axis, and trying to plot this. This was normally distributed. We understood this by looking at, right, whatever this diagram, right? Mean. Here we took 36 apples. There we took 5 only. Think that 5 apple weights. Okay, 5 only, right? And then on the second plot we took 20 apples. 20 apples and took means and then tried to do a plot. So the mean of these means is going to be population's mean, right? The mean of these means is how much? 16 here, 16.03. If you look at the mean of the population, right, it is 16. Known data set. Yeah, as Giri said, right, it is a constant data, right? Constant data, and we have mean is 16. But in real time, population is always ever growing, ever changing. I shouldn't say growing. It may actually entering and exiting people are same. It's going to be same, right? Size is going to be same, but it is ever changing. Okay. So this mean is 16.3 and 16. It is proven. The first point is proven. The population's mean is approximately equal to the mean of all these samples means. Okay. When you take the sample size big, right, the mean of the sampling distribution is almost equal to the mean of the population. If you see this here, sample size is less, the mean is 16.03, population mean is 16, but sample size is big, the mean is actually equal to the population's mean. The mean of the sampling distribution is equal to population's mean. Okay, that is sample. When your sample size is big, it is always good to predict, because the mean is going to be equal to that mean, and whatever, right, whatever the normal distribution is going to be steeper and all that. Okay, the second point is, the third point is, we can calculate a standard deviation of these means. You are getting it, right? Standard deviation of these means, 5 sample means, or standard deviation of 20 sample means, using this formula, sigma by square root of n, or variance is equal to sigma square by n. 25 by 5 or 25 by 5 is the variance, right? Standard deviation is square root of that, right? If you look at this, variance is sigma square. Standard deviation is square root of sigma square. It is sigma, right? But the formula to calculate the variance of this sampling distribution of mean is sigma square by n, or standard deviation is sigma by square root of n. There is no confusion, right? There. Standard deviation is sigma by square root of n. Is it clear? Variance is sigma square by n means standard deviation is sigma by square root of n. Okay. So we can calculate the standard deviation of these means. How do you calculate standard deviation of those means? Let me try to write something on the board. How do you calculate standard deviation of these means? So we have, here, right? I'll take small m1, m2, and so on, m 10,000, right? 5 samples, right? 5 sample size 5, right? I have m 10,000, right? How do you calculate the standard deviation of this m samples? You need to calculate a mean first, right? M, I would say m is equal to m1 plus m2 plus and so on, m 10,000 divided by 10,000, right? That is the mean, right? And then what is the formula for standard deviation? Square root of, I think I don't have space here. So what is this formula for standard deviation? Square root of variance. What is variance? What is variance? m1 minus m square plus m2 minus m square plus and so on, m 10,000 minus m square. Whether you do m minus m1 or m1 minus m, it is going to be equal because square, we are squaring it, right? A minus b or b minus a square is equal to, right? A minus b square is equal to b minus a, right? This calculate the standard deviation, right? Do you agree, Ganga Devi?
Yes, sir.
Right? The standard deviation is calculated like this. Okay. This same standard deviation can be calculated using square root, sigma by square root of n. What is n here? Sample size, right? N is 5. Okay. What is the sigma? Population standard deviation. We know, luckily, we know the population standard deviation. Generally, in real time, we don't know the population standard deviation because we don't have populations, all numbers. To calculate standard deviation of population, what you need? Population's mean you need, population's data you need, each data point. It is infinitely many numbers in population. You cannot calculate this. But this is a sample data set. We wanted to see what happens when you actually take multiple samples from a normally distributed data or not normally distributed data. We have taken a limited amount of numbers. I think Giri is right. Limited amount of data, right? On that limited amount of data, the standard deviation is 5. Okay, we know that. So you can calculate this particular data are these all means standard deviation by using this formula. What is this formula? Sigma by square root of n. What is sigma? 5 by square root of n is, what is n here? 10,000, right? No, n is 20, square root of 20. Sample size is sample square root of 5. Square root of 5. Sample size on this data set is 5, right? So that is square root of 5. When I calculated, right, I got 2.24. Is it approximately equal to this one? This one is calculated using original standard deviation formula. Okay. This number is calculated using central limit theorem's formula. Central limit theorem's formula is what? Sigma by square root of. Got it? Got it? This is approximately equal, right? This number is approximately equal to this number, right?
Yes, sir.
So that is the, when you use, give me one second. When you use this formula, the central limit theorem's formula to calculate standard deviation, you will get a little bit of difference between the original standard deviation and the, the standard deviation calculated with this formula, right? The central limit theorem's formula. Because of that reason, we call this as standard error, SE. You will have this in many places. Especially if you look at a book called statistical learning, or I forgot the book name. Right, in that you will have machine learning and statistics both. there they'll use this term many times, especially linear regression algorithm. When they explain, they use standard error, a term called as standard error. Standard error is nothing but standard deviation of the sampling distribution of means calculated using this central limit theorem. Central limit theorem's formula. It's an approximate value, approximate standard deviation, but it's almost equal to your original standard deviation. When sample size is big, right? It's going to be equal. And I actually physically calculated this number and this number, right? Using the central limit theorem, using the original standard deviation formula, they are equal. When the sample size is big, they are equal. When the sample size is small, they are not equal. So central limit theorem proposed statements are going to be true when the sample size is big. Very true when the sample size is big. Okay. So Gangadev, is your question answered? Still you have confusion?
Yes, sir, I'm clear in that part, but can you please repeat this standard error, sir?
Okay. Standard error is a term given to this formula. You can calculate a standard deviation of the sampling distribution of means, right? Right? You can calculate standard deviation of the sampling distribution of means. How can you calculate? This way, right? This is the original way, right? Do you agree?
Yes, sir.
Right, you can calculate the same number, right? Same number using this formula also. When you calculate this number using this formula, the standard deviation of the sampling distribution of means, using this formula, you call that number a standard error. That's it.
Okay.
There is a different name given to it. It is also standard deviation. There will be a little bit of difference between the original standard deviation and this one. That's where maybe they call it a standard error.
So the approximate value of the standard deviation
of sampling distribution of means is standard error.
Okay, sir.
In general, in your original data population, you should not be using this formula to calculate standard error. On the population or on the sample, on individual sample, you should not be using this. When these numbers are means of samples, then only you can use this formula. Got it?
Okay, sir.
Okay. And you cannot use this formula to calculate population standard deviation. If we already know means, right? Vice versa is not true. We already know all the means, right? We can calculate standard deviation of this, right? Then I'll say sample standard deviation is equal to standard deviation by square root of 5. This I know, right? 2.5. Sigma is equal to 2.4 into 2.25 into square root of 5. I shouldn't be doing this. This is wrong. Right? Vice versa is not true. In a central limit theorem, to find out the population standard deviation, you should not be using this formula. The other way around you can do. The population standard deviation, you can use the standard error formula to calculate sampling distribution's standard deviation. Right? From top to bottom you can do, but from bottom to top you should not be. Vice versa is not true. Got the point? Second point?
Yes, sir.
Okay. So I think Narayana is asking a question and I stopped. Please go ahead. Narayana, somebody is asking a question.
It's actually Shashi.
Shashi, okay. Please.
Yeah, my question was, you're just trying to prove the standard deviations calculated in both the ways, right?
Yes. I am trying to prove and show you that they are approximately equal with examples.
Yeah. That was my question.
Okay. Yeah. I think once after finishing everything, you will understand what I'm actually talking about. that's a problem. Maybe I should change the way.
Yeah.
So yeah, maybe sometimes it is right, sometimes it is wrong. But any other questions?
I didn't get one point, sir. But when the sample size is less, right? Why this is more? I could not get that point.
Why the variance is more?
Yeah, this spread time.
The spread is more, right? Yeah. When sample size is small, right? What happens? You may not get the gist of the population, right? It is like when you take small samples, the average, the mean, right? The mean you got maybe little distorted. Right? When you take bigger sample, right, your mean will be not that distorted. I don't know how to explain, but apple example only. If you take five apples or no, maybe two apples and try to take mean of it, and maybe the 100 apples and take mean of it, you will get more different variants of the apple, right? Then your mean is going to be more appropriate. It is very close. It's going to represent the data a little more appropriately. Got it? It is like this. It is like this. If you are a manager, or if you are a person, and in your hometown or any place you are actually having many friends, or you are managing many people, like political leaders and general public like us, and political leaders. They interact with many people. Like people like us, right, interact with very less people, right? If some task is given to me to manage, and compare it to the political leader, I may not be able to manage it that efficiently, because the mind trained by that person's mind is trained very well with handling many people. He knows many samples, right? He knows many samples, and his mind is very well versed in handling people. My mind is not that well versed in managing people. That's where that person can manage things better, or get the thing done better than me, right? Because the sample size is big, right? The mean, right? The mean is actually close to whatever the reality, right? Reality is what is population. Okay, I'm just trying to give a general example. I don't know whether it matched or not, but did you get it?
Yeah, I got it, sir.
So yeah, the distortion, right? When the spread, right? If you take small samples, five apples you took, all those 5 apples you took are very small. Then what happens? The mean is going to fall here. All the 5 apples you took are very big. The mean is going to fall here. If you take 20 samples, right? However you take, there may be some apples which are actually moving the average a little closer to mean. That's where the spread is less. Got it?
Oh, yeah.
Got it, right? So it is like, this is very important point. Actually, in our machine learning and data science or deep learning also, this we'll use batch size. Batch of number of records we'll take and try to train. If you have 1 million records or 1 billion records, you will not pass all records at once. You will take batch size. When the model is not working well, you need to reduce the batch size or increase the batch size, depending on the situation, whether the model is overfitting or underfitting. If you understand this point, right, it is going to be useful there. Statistics is the basis for AI ML, but statistics is the beginning place. It is just A in the ABCDs, right? Whatever A to Z, it is just the A. Statistics is just the A. There is many things. There are many things in AI machine learning. So we are just learning the basics of it. Okay. Any other question? That's a good question.
Sir, to practice all these things, where can we get the data set, sir?
These things we no need to practice, ma'am. I'll actually show you one two mathematical examples here. If you understand concepts and imbibe them well, right, remember them well, that is enough. We will not do these calculations in our ML. So basically what machine learning, deep learning is doing is automating all these things. Or in another way, we are going to go to mathematical approaches. These are all statistical approaches, right? These statistical approaches end and mathematical approaches start, and mathematical approaches are more accurate than statistical approaches, and more, we can automate them efficiently when compared to statistical approaches. No need to practice these. You need to remember the concept. What is standard error? What is standard deviation? What is normal distribution? What is mean? What is sampling distribution of means? Right? All these concepts you need to understand. What is, we'll see some more. What is p-value? What is statistical significance? These are all theoretical things you need to remember. Understand and remember. Okay, I'll show.
Okay.
I'll show one or two mathematical examples also in the class of tomorrow's class.
Okay, sir.
I think you are getting it well, right? That is good. So generally, right, people get confused in these inferential statistics classes, right? People get confused. If you are not confused and stable, right, that means you are you are in right path. And I am able to explain it well. It is the problem with me generally, not you. So any other questions?
Yeah, Rama, just now you said that we cannot calculate the standard deviation in the reverse way.
Ah,
So when in a problem, let's say we have a standard error and sample size. So can we calculate the standard deviation of the population?
no, we cannot. We should not.
Okay.
We should not use standard error. So, standard deviation of the sampling distribution of means. And anyway, we'll know the sample size, right? By multiplying these two, you should not be calculating population standard deviation. This is, you cannot, you should not. What you do in the situations is, you will take a best approximation of the population and try to calculate a standard error. We'll see that example. Your question is very right, and we have an example for that. That is where you call it as statistics. Statistics is always not about the perfection. It is about what best you can do, right? This is statistics is all about what best you can do in a given situation. It is not about perfection. Mathematics is all about perfection, right? But statistics is not like that. What best you can do.
Yeah, Rama, one more question. Like my understanding here is which standard error is less? That is the correct sample data set, right?
I didn't get your question. I
For
think.
example, see here two examples, standard errors.
Mhm.
If you take that 5 and 5, it is 2.24. If it is a 5 samples with 20 apples, it's 1.12, right?
No. 5 apples with. I didn't get that. I think you understood it something wrong there. What are you thinking about this?
I think 5 samples with 20, right?
No. 10,000 samples with 20 apples each.
Okay. 10,000 with
10,000
20,
samples
yeah.
with
Yeah.
20 each. 10,000 samples with 5 each.
Hmm.
Sample size is small. Number of samples are same. In both
Okay.
cases, number of
Hmm.
samples are 10,000 only.
Okay, got it.
So this 5 is the standard deviation of the population.
Standard deviation. Yes.
Divided by square root of sample size.
Hmm.
The sample size is equal. 10,000 samples, each sample size is equal.
Yeah.
So one point you need to remember is statistics is not about perfection. It is about what best you can do in a given situation. Because I'll go to an example now and show you the math, and there we'll do weird things. So that's where I'm actually preparing the ground. Okay. So I think let me go forward. If you have any questions, we can come back and then answer them. So on
Yeah,
the
sir,
not normal. Yeah,
sir, one
please.
small suggestion on the previous slide. Yeah, here. Maybe because the 5 is the standard deviation for the whole population, and in the first example, even the sample size also 5. It may be confusing to people when they watch this one in isolation. It's better.
Sir,
It's better
I
to
think
change.
I know I got it. I cannot change because this tool is not working on modern whatever latest Internet Explorer. This
Okay.
tool is
Sure.
using applet,
Okay.
right? And it was built by somebody else. And when I started training, I was able to run it once on my machine, and the new machine was not working. So I took a recording of it and screenshots of it, and then I think I'll put some. I used to have the URL also somewhere. I know that maybe I can show you that. Maybe you can actually try it. So central. I think your point is right. I never noticed it. When Narayana was asking, right? I got to know the same thing, but we may not be able to. Stats book. This is the one. This is the one. You will have a tool in this. simulation basic. So this is the one. Yeah. So original Java version. You can download this and try to install it on latest machines, right? It is not going to work. On latest machine, right? It's not going to work. So try to experiment with that. You can download this, right? Version not requiring Java. Okay, version not requiring Java also is there. So you try to do that. Okay, I already did it, and this is the one. This is the site. Okay, so if it is running on a new machine, right, I'll change it. I will see. Okay, that's a good suggestion actually. But now it's a time-taking effort, I think. Okay. So anything else? Anything else on that? I said that I am not going to change it now. Sorry for that, but because of the tool problem, it's a old tool and it's not going to work. So the next thing is inferential statistics. We need to understand what is confidence interval also. Okay, so we understood what is standard error, we understood what is sampling distribution of means, and we understood central limit theorem. We will use central limit theorem and try to solve one problem. Okay, this problem we'll try to solve. Along with that, we'll understand what is confidence interval. In general, right, when you look at exit polls, right, if only one constituency elections are going on, then the exit poll companies, they'll say, like, a person is going to win with 14,000 votes. We are, with range between 14,000 to 17,000 votes. We are 95% confident, they'll say. Have you ever observed that? Have you ever observed it? They'll say, in a range, right? 10,000 to 20,000 votes majority, and we are 95% confidence, they'll say. Have you ever seen that in the newspapers? Yes, no? No?
Yes.
So that number, right, the 10,000 to 20,000 is the confidence interval, and the 95% is the confidence score. Confidence score we call it as. Okay. So for confidence interval, there will be three numbers: minimum value, maximum value, and the percentage. How confident we are about that range. Okay. So why that range and why that percentage we'll see today. Okay. So with a simple example, suppose that the example is, so I have a sample of 36 apples from a farm. Okay. The total number of apples are 2 lakh apples. Total apples are from that farm are 2 lakh apples. I have a sample of 36 apples. Okay. The mean weight of the sample is 112. These 36 apples mean weight is 112 grams. Okay. And with a 40 gram sample standard deviation. 40 grams standard deviation, mean is 112. Okay. We need to calculate, right? We have 2 lakh apples and we have one sample. We know the mean of that sample and standard deviation of that sample. We need to find out what is the probability that mean weight of all 2 lakh apples is going to be within 100 and 124. All these 2 lakh apples, mean weight is going to be between 100 and 124. We need to find out. Just by looking at this sample's mean and this sample's standard deviation, we need to calculate the total data's mean weight. What is the probability that it is going to fall between this range, right? So this is what I said. Statistics is all about what best you can do in a given situation. It is not about the perfection. What is the given situation? I have one sample of 36 apples and I know mean of it and standard deviation of it. I need to find out the probability of the total population's mean is going to fall between this range. Okay, so this is a very tough situation, right? So we'll use central limit theorem to find out that. So let me make some statements here before we move on. Right. So we have 36 apples, right? Right. So these 36 apples, if 36 apples weights are normally distributed, right? If 36 apples weights are normally distributed, if I say 36 apples weights are normally distributed, what should I take on x-axis? What should I take on x-axis?
Weight.
Weights, right? Weight
Yeah.
1, weight 2, weight 3, and so on, weight 36. Or maybe, you know, all weights may not be distinct. So we'll have maybe 10 weights, maybe 5 weights, right? 5 different weights. Weight 1, weight 2, and so on, weight 5. All apples may fall into either weight 1 or weight 2 or weight 3 or weight 4 or weight 5 bucket. Okay. Then if the data is normally distributed, maybe less weight, there are less number of apples. A little more weight, there are a little more number of apples. A little more weight, right? Like that it's going to be, right? So number of apples on y-axis, okay? Number of apples on y-axis. If data is normally distributed, we say the mean is going to be 112, right? We said the mean of these 36 apples is 112 and standard deviation is 40, right? When I say standard deviation is 40 and if the data is normally distributed, 68% of 36 is how much? Let me calculate. 3 sigma rule. I am actually trying to reiterate that 3 sigma rule one more time so that you will remember well. 68 into 36 divided by 100. Why am I calculating this? Anybody can tell me? 68% of 36 apples. Why am I calculating this?
So how many apples fall on in that range?
Within one standard deviation. Within one standard deviation. What is one standard? Within one standard 24, right? What is within one standard deviation? Can you tell me within one standard deviation? What is?
One standard deviation means, yeah, go ahead.
Go ahead.
From mean, it takes one standard deviation to the left and one standard deviation to the right.
So what is one standard deviation to the left is 72, right? 112 minus 40 is 72.
40, yes.
Okay. This is 130, 152. Right? What is this 72? What is this 152? Weight of the apple, right? Grams.
Yeah,
72 grams and 152. That point you need to remember. Always when you are actually solving a problem, you should get connected with the business. Right? What is the business here? Apple weight, apple weight, apple weight. All the time apple weight. Right? So there will be 24 apples which will fall between 72 and 152. Right? So I can say, right, 68% confident that the apples, apples within 24 apples are going to be within 72 and 152. Can I say that? I am 68% confident that there is going to be 24 apples or there is going to be the weight of the apples, there are going to be some apples. 68% of the apples are going to be within this range. Can be said as 24 apples are going to be within this range, right? I can say that, right? Either that statement or this statement is same, right?
Yes.
Right? I can say that 68% confident that the apples weights are going to be within this range, right? 72 to 152. 68% confident because data is normally distributed and within one standard deviation 68% of the data. 95% of the data is going to be within two standard deviations. 36 apples, 95%. I don't know how much we can calculate that. Is going to be like that, right? So when data is normally distributed, you can actually get those inferences. You can actually calculate the probability. Is that point clear? When data is normally distributed, you can calculate the probability. Is that point clear? Because of the 3 sigma rule. 68% is probability, right? 0.68. Because when you take normal distributed curve, area under the curve is going to be 1, right? Is my point clear? Can I move on?
Yeah.
Okay. When data is not normally distributed, can we will we be able to find out this percentage? When data is not normally distributed, will we be able to find out this percentage? Yes, no?
No.
No, right? No. So, do we know that this 36 apples are normally distributed? Anywhere in the statements they gave, whether this is normally distributed or not?
No.
No, right? So we don't know whether these 36 apples weights are normally distributed or not. Okay. But from central limit theorem, what we know? If you take 36 apples, many samples, if you take 10,000 samples of 36 apples, those 10,000, let me take another color for this. Right? Those 10,000 apples, 10,000 samples, 10,000 samples of 36 each, those means are going to be normally distributed, right? Do you agree? From central limit theorem, what is it saying? If you take many samples of 36 apples, right? Those weights, those mean weights, right? mu1, mu2, and so on, mu maybe, maybe 10. And all these 10,000 samples of 36 apples may fall into, 10 buckets. And then that is definitely going to be normally distributed. Do you agree?
Yeah.
Right? This is definitely going to be normally sampling distribution of means is going to be normally distributed. Now we will assume something and try to derive the probability. Okay, right? So when data is not normally distributed, or we don't know whether population is normally distributed or sample is normally distributed or not, we will take the central limit theorem's help. We'll take another example tomorrow, which is going to be more solid. Right? This is like we don't have anything and we are trying to assume something and try to build. Okay. Need. What is the need? What is the need we need to, what is that we are trying to find? The mean weight of the apples, okay, is within 100 and 124. We need to find out the probability of the mean weight of the, so when you take n number of samples and means, you actually need to find out the mean only, right? So the mean of the population you need to find, right? When you take 10,000 samples and take mean of all those means, that is equal to the population's mean, right? So that is one central limit theorem rule. So what we have is sample size 36, sample mean 112, sample standard deviation 40. Okay, we have very little information. Okay, so we will assume. So let us use central limit theorem to derive an approximate probability from the range. So now what we will do is, to use central limit theorem, we must make some assumptions. What are the assumptions? First assumptions: took many samples of 36 apples. Suppose that I took many samples of 36 apples. And then second assumption is the sampling distribution's mean is 112. We know only one sample's mean, right? We're assuming that all these samples mean is also 112. Okay, all these samples mean is also 112. Because we don't have any information, we are taking it. Whatever we have, we are taking it. And population standard deviation is also 40. We know only one sample standard deviation. And we are assuming that population standard deviation, best approximation. Best approximation of sampling distribution of means, best approximation of standard deviation of the population. Any questions, concerns? Any questions, concerns so far? Right? I am talking very illogical. What questions you will have? I took samples mean as the sampling distributions mean, and I took sample standard deviation as population standard deviation. That's how in statistics it is calculated. That's where it is an approximation. It is always prediction. It is not the exact thing. It is not mathematics. It is statistics. Okay. It's also a branch of mathematics, but when I say mathematics, right, not like linear algebra or any other algebra. Okay. So now if you assume that we have taken many samples and we have means, it is actually normally distributed, and we are saying the mean of these means is 1/12, right? And then you can calculate the standard deviation of this particular graph, sampling distribution of means. How do you calculate? Population standard deviation divided by sample size. Population standard deviation, we assumed it as 40, right? 40 divided by square root of 36, sample size. 6.67 is the standard deviation of this sampling distribution of means. Okay, when we know this, 30, the 68% of the samples are going to, 68% of the data is going to be within one standard deviation. So the mean of many samples, right? So 105 and 118 are the mean weights. This is what? The mean weight, right? The mean weight of apples. This is also mean weight. 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 So there is going to be 68% of the data which is going to fall between 105 and 111. Okay. There is going to be 98.66 and 125.34. 95% of the data is going to be within. So we can say almost 95% confident that the apples weights, the mean weight of the total apples is going to be within this range, 100 and 124. This is close to 100 and this is close to 124, right? The 98 is close to 100. 124 is close to 125.34 is close to 124. What is the question we are trying to answer here? Probability that the mean weight of the apples is within 100 and 124, right? This is what we are trying to see. When we assume all these things and see within 2 standard deviation, the range is falling. So approximately 95%, right? The confidence interval, right? 100 and 124, we are confident that 95, right? Around 95% of confidence is there that the population's mean is going to fall between 100 and 100. Why? Because many of the apples means are actually within this range. Do you agree? Many of the apples means are going to be within this range, right? 100 is around here, right? 124 is around here. So it's going to be around 94%, 94% confident. Did you get it? Confused? Did you get it? Everybody is silent. That means nobody got it.
Sir.
Right?
Yes, sir.
You got it? Got it?
Sir, one question is just going back to this 68% and 95%. I remember you telling us some formula which give us these numbers, like 1 standard deviation it will be 68% and 2 standard deviation 95%. So that's the density function.
How did I got these numbers, or you are asking about these numbers?
No. I'm talking about 68. The number 68. Number 95%. So these things from the probability density function, right?
No, they are thumb rule. It is thumb rule. When data is normally distributed, it is given that 68% of the data is going to fall within one standard deviation.
Okay. No, I
So
thought
what is data
from
here?
some formula.
No formula. It is thumb rule. When data is normally distributed, it is a thumb rule that 68% of the data is going to fall within one standard deviation. 95% data is going to fall within 2 standard deviations. 99.7% of the data is going to fall within 3 standard deviations. When I say data here, what is data? Mean of the apples is the data here, because it is a sampling distribution of mean. So mean of apples is going to be within 105 and mean of apples is going to be within 105 and 118, 68%. 68% of the data, right? 95% of the means of apples is going to be within 98 and 125, right? Around 94% confident. So we can say the confidence interval 100 and 124, we are 94% confident. Can we calculate the exact percentage? Yes, we can. I'll go to that in a minute if you understand this. You got it, right? It's all based on these 3 assumptions, right? And using central limit theorem, right? when data, we don't know what is happening with the data, we always try to take sampling distribution of means, because sampling distribution of means is normally distributed. We have 3 sigma rule. We can actually find out something when you know 3 sigma rule, right? Got it? So we can calculate the exact percentage also, right? I'll explain this tomorrow. Maybe I'll recap. We'll start with the recap and then I'll explain this tomorrow. Right? This is not needed for MLAI, but this will actually make your concepts stronger, the normal distribution. Now you are asking, right? How did I got the 68, 95%? Right? So we are actually going back and forth so that, you know, you remember the concepts well. Okay. For that purpose, I added these. Now maybe 4 or 5 classes, right? These 4 or 5 classes of these inferential statistics is all about making your concepts stronger. Even if you don't understand, don't worry. Try to feel free, ask questions, right? I'll explain that multiple times. Okay. I'll stop here today because I think